Good morning. Can you hear me okay? Good. Okay, thanks. I usually have a softer voice, so I'll use the microphone. I'm Michael Littlecrow. I'm substituting for Professor Arthur. He was my mentor the first year. I came here 5 years ago, and this is the first opportunity I've had to repay him. So hopefully I do a good job for him and keep you going, keep you learning while he's taking care of something else. I don't know. But anyway, he asked, here I am. So you guys are engineers, is that right? Or science, right? Engineering. I taught this class last fall. I usually teach the business sector, the calculus, but I did this one. This is one of my favorite sections. It's also one of maybe the harder one. You won't learn anything necessarily new about calculus. What you learn is a problem-solving approach to applying calculus concepts. Okay, so the concepts we will be talking about today, you've already discussed in 4.1 and 4.3. So we're going to take those and we're going to solve some problems with them, which is what engineers do, right? You solve problems. So what we're looking for, when we call it optimization, we're looking for what's the maximum or the minimum return. Again, in business situations, that's, you want the minimum cost or you want the maximum profit. Engineering, maybe you want the most efficient use of the fuel, or you want to bring in your creation at a lower cost, those types of things. But whatever we're going to look at, we're looking for a maximum or a minimum. So we're going to use the concepts from 4.1 and 4.3. Talking about absolute maximums and mins, and basically the hard part is setting up the solution path. And even from the textbook, it says that the greatest challenge is often to convert the word problem into a mathematical optimization problem by setting up the function that is to be maximized or minimized. So this one, the hard part is you just got a bunch of words, you've got to get it all set up. So what you're going to be drawing on is all the mathematics you've learned for the previous 16 years, geometry, formulas, and stuff. You're going to have to pull those out, get it set up, and then the calculus part will be pretty straightforward, like what you've already been doing, taking a derivative, finding where that first derivative is 0, which tells us we're at a place where we've got a horizontal tangent line, right? And we have either a maximum or a minimum, and then we have tools that help us decide whether it's a max or a min, and we got our solution. So the calculus is the easy part. The hard part is getting it set up. So, and this is just from the textbook, but there's sort of a 6-step process that, although when you're solving problems, it's usually not a linear process of 1, 2, 3. It's a circular process. So first, work to understand what the question's asking. And when I do that, you'll see I oftentimes will read the question backwards. And when I mean that is I will look for the last sentence first, because that's usually what the question is. If you know what the question is, it's a lot easier to understand how to set it up. The thing is sometimes you get reading something and you get distracted because you start thinking that the question is going to be this and it's actually that. So read the last question first. If you're good at doodling, that's where this is. We draw a little diagram, try to understand the question as we're going, and notice so number 2 actually ties back to number 1. And then we have to introduce some math notation. This is finding an equation, a formula, something of those minds. And the important part, especially in engineering, is to label what we call X, label what we call Y, or whatever variables we use, label them so that we get down and we get our answer, we know what that means, right, if we've labeled it. And we express things, and usually they talk about Q because we're looking for some kind of quantity of something that we want to either maximize or minimize. And then we get it all set up. That's again, the hardest part. And then once we move forward with all the variables, we start using our techniques, get the formula set up, and then use the calculus, basically take the derivative, right? Set it equal to 0. That's going to give us where the maximum or minimums are. And again, depending upon what function we have, there's going to be different techniques that we'll have to use. There's square root functions, there's exponential functions, there's linear functions, so there's all these different techniques we'll tie in to get to there. So today we're just really going to look at a lot of different examples of how to set things up, how to set up a question, and then how to move into optimizing it, figuring out whether they want a minimum or a maximum. Okay. So we have two derivative tests. Our first derivative test, certainly if we set it equal to 0, we find out where those minimums and maximums are, because that where a derivative is equal to 0, that means we have a horizontal tangent line, which means that's the height, right? It goes up and it comes down. The first derivative test, we know if we went up and then came down, what kind of a value do we have? Up and then down, we've got a maximum. If our derivatives were negative and then positive, we went down and then came up, we got a minimum. Okay, so we could do all of this with just the first derivative test. It'll work. However, we also, assuming I wasn't here, but you should have also learned a second derivative test. Am I right? Okay, good. The second derivative test, you don't have to use it, but it's helpful sometimes. If you take the second derivative, if it's positive, and I always think of this is how I remember a positive things make you smile, and when you're smiling, you get a minimum, right? Because you get a U shape. If your second derivative in any particular area is negative, you're going to frown because negative things make you unhappy or sad, makes you frown, it's concave down, and you're going to have a maximum. Okay, and I have to think through that process because sometimes I'm dyslexic, and so I will mix them both up. And I think, oh, positive means a maximum, negative means no. You got to think through the process. Positive is a smile. It's going to give us the U, so we get the minimum there. Negative actually is where we get the maximum. Okay, so think through those steps. And then here's just sort of a little bit of a review. So the first derivative test, if we have a positive first derivative going to a negative one, we went up and came down. That gives us a maximum. Just some pictures to remind us. If it went the other way, we were negative and then positive on the first derivative. Again, you just check a couple points on either side. Then we're going to have a local minimum. So we could do all of this without graphing. And I make mention of this is when I learned all this stuff back in the early 80s, we didn't have graphing calculators, and it was sort of like we were going with a blindfold on because we couldn't see the graphs. We had to use all this stuff. You have the fortunate to have the technology where you can always graph them, right? You've got a graphing calculator. So you can also, and I highly recommend that because when, seeing is believing type thing. So if you graph it, you'll also see it, and you'll confirm these things. Okay. It is possible that we end up with that when the first derivative is 0, occasionally sometimes that's an inflection point, so it's neither a minimum or a maximum. So that can happen, so we kind of look for that. And that's what happens when we look to either side of that point and the derivative doesn't change. It's staying negative or staying positive. It means we found an inflection point, not a min or a max. So those happen occasionally, but not with a lot of regularity. Then the same thing we can do, the second derivative test sometimes is a little bit cleaner. Again, we don't have to choose a particular point. We could actually even choose the maximum or minimum point we found, and we just plug that in and find out in the second derivative, is it positive or negative? It'll tell us concave down or concave up, depending upon which way it works. Okay, so that's, again, an option. If you didn't know the second derivative test, the first derivative test works perfectly fine. So again, we teach it to you, but you get to decide which one you want to use. So something like 3x squared, everywhere, actually you could just plug in any value for x, it's going to get squared. It's going to be positive everywhere if you take its second derivative, right? Second derivative is just going to be 6x will be just 6, right? 6 is a positive number. the first derivative, and then the second derivative. Second derivative 6, it's positive everywhere, it's concave up. That means we would have a minimum, so that's kind of clean. If we have this function, take the first derivative, negative 6x squared, and then take the second derivative, negative 6. When we look at the graph, it's negative, the second derivative is negative everywhere, it's always concave down. Okay, so again, sometimes it's a nice tool to have in the bag, and there's places where it's actually easier to use than the first derivative test. First derivative test, you'd have to take derivatives on both sides of where the derivative equals 0. Okay, so it's maybe a little bit extra work. This one, you have to take that second derivative, but again, when it's a constant, it gives us our answer right there. Okay, so are you ready to get into the section, start into some problem solving? Yeah? Okay, good. At least you are. Okay, so here's where we're going to start kind of using the process. Again, I don't go step by step necessarily, but I sort of start a rectangle as a perimeter. And then what I see is, okay, there's not one thing. They want to actually find three things. They want us to find a function for the area. They want us to find the dimensions of the rectangle that maximizes the area. And then they want to find the maximum area. So again, we're thinking a rectangle. What does a rectangle have? It has what? 4 sides. 4 sides. Are they all the same sides? No. Could be if it's a square, but yeah, 2 will be the length, 2 will be the width. So we could start thinking of variables as we go through this. And we're told that the rectangle has a perimeter of 92. So that's what we call a constraint. So everything we have in here, there's a constraint, and then there's something we want to maximize. So if we can bring out what those are. The constraint is, it limits our ability when we're solving this. So we have a constraint here. And we look for the word of maximize or minimize. There's that. And so we know that what we're optimizing is the area. Yeah, we don't have to rewrite it. That's what we're going to maximize. Okay? So right now, we dig back into when we had geometry. When was the last time you had geometry? Maybe you had it in high school. Maybe it was at grade school the last time you had geometry. But what comes to mind when we talk about perimeter? Length times width. Oh wait, no. 2 times the length, or the width, whichever. 2 times the length plus 2 times the width equals our perimeter. Okay, so good. That's something we're going to need. Oh, we're using L and W. You could use X or Y. So this is a good place once we start thinking through things. L will be our length. And W will be our width. So I labeled that just so, I think I'll remember L and W, but that's why if we chose those. If you chose X and Y, you choose which one you want to be which. And in this case, to start setting things up, we know that 2 times the length plus 2 times W needs to be equal to 92 feet. Okay, so we're actually getting things set up just by kind of analyzing. Now we're supposed to find a function for area in terms of width. Oh, they said width should be X, but I don't always listen to what they tell me because, hey, we get to decide. We're going to call it width W. Because I'll forget what X is, let me just call it W, right? And you could do that. That's what the nice thing of, you're going to have this. So what is area? We think of perimeter. Area is length times width. Simple thing, but again, we have to remember, and sometimes it's digging back in the past, and sometimes we mix these things up, but area is going to be length times width. Okay. So we're well on our way. We've got some mathematical formulas here. We have a constraint function, and we have a function that we want to maximize, or to optimize, I'll say. We want to maximize it, and oh, we're in good shape. We've actually already done, almost done step A. But one of the problems we have with our area function is it got two variables. And we aren't very good at doing math with, in fact, we haven't gotten to multivariable calculus yet, have we? I think that's like Calc 3. And I don't thrive on multivariable stuff. So how can we get it to be one variable? Excellent. We go back to that constraint function. It's very valuable to us because we've got two variables in there, yes, but we can solve in terms of one of the variables, and now it's a function that we can substitute, and our problem is solved. So do you want to solve the perimeter? Do you want to solve it for L or W? It doesn't really matter. But for W? Okay. You'll find, well, anyway, this kind of works backwards, but let's do it. So we're going to solve it for W. So we would subtract 2L from both sides. Right, so this becomes 2W equals 92 minus 2L. And I love it when the problems for perimeter give us an even number because we're going to divide by 2, right? And so it makes the number a little bit nicer. So then we divide both sides by 2. Actually, we divide everything by 2. So we come up with W equals, what's 92? 46. Thank you. That's the other things. When I'm in problem-solving mode, my arithmetic becomes it really sucks sometimes. So you got to keep me on track here. Okay, there we go. That's why I like calculators. When I'm problem-solving, just plug it in the calculator because the mind, it's two different parts of the mind that comes up with that stuff. So that we're going to use. And what are we going to do with that? We're going to take that as our W, and we're going to plug it in here. So then we get this function that area equals length times 46 minus length. Now we've got the function. So this is really the answer to the A part. It is a function in one variable, just the length, how we would maximize the area. So we have done A. Not too bad. Next one, we're solving for two things. So we solve for the dimensions, solve for what length is and what the width is, so we'll come back to that. And then it's an easy step for the next one. So what should we do next? What's that? Take the derivative, but if we do the derivative of this stuff, we've got a product rule thing, right? What if we distribute it first to kind of simplify? And again, you could go with the product rule. That's just like the heavy lifting stuff, and I like lighter loads. So we'll distribute this, and we get 46L minus L squared. And hopefully you start recognizing this as a quadratic. If you go back to your algebra, quadratic with a negative in front is going to be concave down. So you kind of, okay, so this will give us a maximum. Again, you could also graph it and just find it, and it's going to be at the vertex. So you could use algebra to solve it at this point, but we would, using calculus, because it's a calculus class, let's go ahead and take the derivative and set it equal to 0. Why do we do that? Because we're looking for where is the tangent line horizontal. That gives us a minimum or a maximum. So next step, take the derivative. And I apologize if my notation is a little different than Dr. Arthur's. I'm not sure which one. There's two different notations, right? I could have called that dA, dL or something, but I like the prime notation. So derivative of 46L is just going to be 46. The derivative of L squared is negative 2L. We've got our derivative, set it equal to 0. So this is the next step up here. Let's go ahead and change colors. So we're going to say, where is this derivative equal to 0? And notice, after this, it's like the math is not so bad. The hardest part was getting it all set up, just like the book said. Solving for L, you could add 2L to both sides. It's kind of a little bit of a shortcut. And then we divide both sides by 2. So you get L, and it's 23. I can do that one. Okay, 23. We're halfway there. We got one of the dimensions. Okay, so we're looking at this B question. Find the dimensions. Okay, so we need L and W. So I found L equals 23. Oh, there it is. That's how I find W. Come back to that constraint function. We solved for W earlier. Then we get 46 minus 23. Oh, that's also 23. What does that mean we have? We have a square. And you'll just see, if with all things being equal, a square maximizes area for a rectangle. Now sometimes we'll see ones where it doesn't end up being that, because like there's fence and one fence is more expensive than the other, so we don't get a square. But all things being equal, maximum area is achieved with a square. Okay, so that's the answer to B here. Let me label these. This here was our answer to the A part. This is our answer to the B part. And C, find the maximum area. What's left to do? Go back to the A part. Take our, well, actually we could go back before the A part. Here's our areas, length times width, since we have those. So area is equal to 23 times 23. And could I have a little help with that? I'm not going to do that in my head. How much? 1,024. And there's the C part. Okay. But again, solving this particular problem isn't, you know, look at the process of what we went through. Think, you know, the thinking.
529.
Oh, it's 529? Okay. Let's come back here. Oops, wrong. I want the eraser. Just 529? Okay. Check it on the, yeah. Is that good? Okay, checks. All right. Now, are you ready? So this is a warm-up. This is like the easy ones. We're going to go to ones that involve more. And this is one of my favorite ones. I teach also math for elementary teachers, and we do this one with elementary teachers. It uses a concept. I've done some work, educational work in Thailand as well. We did an education abroad. When I was there, I also taught in Kazakhstan for a year. And the British programs, the mathematics, they teach something called nets. Let me get through this a little bit here. What a net is if you take a flat piece of paper and turn it into a geometrical shape, that's called a net. England, they're doing this all the time. And so anywhere they have British curriculum, they know about nets. American curriculum, I never did this stuff. How about you? You did? Wow, maybe they changed the curriculum in 40 years. That'd be great. These are great things to do. So if you understand it, great. If not, well, that's what we're going to work through. So we're taking a flat piece of paper, cutting out some corners. It comes a box. In here, let's see. Let's go here. They came up with this. I also teach the pre-calculus class in the 170, the pathways version. They came up with this, so I borrowed it from them. They've got a little applet, once it loads, that will actually sort of demonstrate what's going on. And I don't know if I sent this to Dr. Arthur. I don't know if he'll post it or not. If you want it, you can always send me an email. I'd be happy to share this with anybody. But what this does is, notice we've got this here. We can actually change the amount of the cuts, and it'll graph it over here. We can actually fold these up so you can kind of see if you cut those corners what kind of a box you get. And if we click on these, we can show the point. So here's, I can see it, there's sort of a maximum, and we can see volume of the box, length of the cut. We can also trace that point so that I can see there's a maximum point there. That's sort of what the graph would look like. And then here's my box. Okay. And again, if I make the cuts bigger, I get a taller box, but it's actually got less volume. So you can kind of play with this a little bit and see what's happening. There's a place where it will maximize. Comes down. Kind of looks like it's going to be quadratic, right? But if you remember about volume, how many multiplications are involved in volume? 3. So if you see this, it's actually going to be a cubic. So there's this solution. There'll be another solution over on the other side, which would be sort of like an imaginary, because you can't do a negative cut. So it's actually quadratic or cubic, but that's okay. So this sort of a little bit of exploration, understand what we're getting at, what we're doing. And now let's come back to so that's just what this slide's about. This is what we're doing. We're going to cut out the corners and, let me back up. Come back to this. So as I make the cuts, let me not fold it. Let's leave it unfolded. Show the segments. So what's happening? Let's focus on the width. I think that's purple. So without the cuts, there's the full width. And then how is the width getting shortened if we call those cuts each X? There's an X on each side, right? We're subtracting off an X so there's going to be a 2X. This is the hardest part to kind of see. A lot of times you first do this, if you haven't seen this stuff, you just, the width minus X, right? Because you're cutting an X off. But you're cutting 2 X's off there. And same thing will happen with the width, is the width gets cut down by 2 X's. Okay. All right. So let's go ahead and come back here. So now we've got a question here. Again, I looked sort of to the end. I've got 3 questions. So we need to express the volume as a function, just like the last one, the area. Okay, we'll get the function. It'll ask about the domain, because again, that's that thing, you can't have negative cuts, right? And how much can you cut? Can you cut more than the paper you have? You have 8 inches. No. In fact, you can't even cut 8 inches, right? Because you're coming from both sides. You could only cut 4 inches. And then so kind of gets you to think of that. And then find the dimensions to maximize the volume. Now notice this question, we don't have to get the volume. That's kind of cool. We just need the dimensions. Okay, so what do we have up here? 6 foot by 4 foot, 14 feet. What do we call that one? That's our constraint. We don't have an infinite piece of paper. It's got some limits. So those are constraints. We're going to use those in some form. And that will give us something. Okay. Squares of side length X. Okay, we'll go with the X with this because they suggest a variable here. Will be cut out of each corner of the cardboard, and the sides are folded up to create a box. And again, if you got this in the book, there's no picture, right? So what am I doing? That's why we showed the other picture. So we're going to cut out the corners, fold up and make a box. So we know over here, maybe usually we call the length the longer one. It doesn't matter, the width and the length, right, of the piece of paper. So maybe we start drawing something over here. And it's not quite to scale. We call this 6 feet. We'll call this 14. And then what they want us to do is cut out corners. And this is what, once you work a few of these, you'll see, at least geometrically, there's only so many things we can make and do. And then you they become very similar, and you kind of know how to approach these. So we're going to call this little thing here X. We'll call this the length. We'll call this the width. Okay. So where do we start? Do we need anything about area? I've got a 16 by 14. Should I calculate the area? No, they didn't ask about area, so there's a question we don't need to answer. But they are asking about volume. What do I need for volume? Length times width times height. So okay, now it's starting to click here. So notice we're doing this one a little bit backwards. The other one we set up the constraint function first. This one, I think it's easier to go to the optimization function, which is length times width times height. And then over here is thinking again, going from the paper when I fold it up, what is this new length going to be? Started out at 14, but I cut x's off of each end, so now what is its length? 14 minus 2x. And the same thing with the width. It started out being 6 feet, but I cut 2 x's off the sides, so it's now going to be, when it becomes a box, it's going to be 6 minus 2x. So I've got those. What's going to be the height of the box? X. The amount of the cut is when you fold it up. Sometimes you won't see that unless you've actually done this. You could take a piece of paper, cut off, X, whatever I cut it, that's going to be its height. So I come over here. So we kind of use those constraints, are kind of built in here. It's a little different feel though than when we were doing the perimeter problem, where we could probably, it was easier to set up the perimeter first, the constraints, and then from there we go. But notice also the cool part about this, we got our optimization function set up. In setting this up, we have each of these variables equal to x. We have one variable when we set this thing up. So in a sense, that's a little bit easier. We don't have to solve, we don't have to do extra work. We can now come over to our volume function and, well, actually make it a function. The length, 14 minus 2x. The width, 6 minus 2x. And the height, x. Cool. Got our function. We want to maximize it. We've got it down to one variable. Now, usually this is actually a little easier to teach in algebra class because we could just now graph it with algebra, find that maximum, and we're done. This is a calculus class, so we want you to take the derivative, right? That's not a real pretty derivative to take, so what do we kind of need to do first? Distribute, FOIL, all this. So that's a little bit of algebraic stuff. I think I'll FOIL first. So let's go, because I'm going to need some. 14 times 6 is 60, 70, 84. And then 14 times negative 2, negative 28, x. And then we take 2x times 6 and get a negative 12x. And then negative 2 times negative 2, which gives us a plus 4x squared. All of this times x. I will kind of sort of simplify, and at the same time I'm going to distribute this last x. So 84 is by itself, so I'll call that 84x. Negative 28, negative 12, that's 30, that's 40, negative 40. It's x, but then this x comes through and we get an x squared, right? And then this last one, 4x squared, becomes plus 4x to the third. Does that make sense? So I kind of did two steps at once, simplifying the boiled part and then distributing the x. But it's a lot easier to take the derivative now. So I can say the derivative of v is going to be 84 minus 80x plus 12x squared. Did I get that right? Okay. What do I want to do with this derivative? Set it equal to 0. And you know a quadratic's going to have two places that equal 0 typically. So we'll have probably both a minimum and a maximum. One will be negative and won't make any sense. One will be, it's actually, I'm not actually even following their directions here. I'm just jumping in and solving it. Actually, we did A, so let's celebrate. This is A here. B, we'll worry about it later. Because it actually makes more sense when we get our answers, right? We're going to get one negative, and we have to recognize that that negative cut doesn't make any sense. It's not in our domain. So, again, you can take a graphing calculator, solve this, where it's equal to 0. You could also factor. Let's see, what goes... Just 12 goes into 84, but 12 doesn't go into 80. So we're going to set it equal to 0. How's this going to factor? So 80 divided by 4 going to be 20. That's going to be 3. Okay, that'll work. So I can factor out a 4 from each of these, and that will leave 22. No, 20. Let's see. 21 minus 20 plus 3x squared. And then we could divide both sides by 4, and that's not important, so we got something smaller here. Let's see how this maybe factors. I could go with 3x, and I could go with x. That'll give me the 3x squared. 21, I could do 7 times 3. Does that give me the proper, let's see, 7 and 9, that's not going to work. I could also, 7 times 3 is 21. Does this factor? Maybe not. I don't think this is going to factor very well. Yeah. So then that means we got to use a quadratic formula. Oh, that's ugly. Well, if we got to use a quadratic formula, that's algebra. I think it's okay to use a graphing calculator. So let's come back here. So let's just graph it. And remember, we're graphing the derivative. So we're looking where the derivative is 0, and so that's going to be an x-intercept. So what did we have? We got it down to 21 minus 20x plus 3x squared. Incidentally, I worked with a colleague of mine over at, I used to teach at Scottsdale Community College. He was an engineer who became a math professor. He told me in engineering, he says, they don't want to see your handwork, they want to see you ran it through a computer or a calculator. They want to see a machine did the final calculation, because they know humans make mistakes. Computers only make mistakes when humans put it in the wrong way. So anyway, that's, engineers will go with that. So then let's get the graph. There we go. Well, looks like they're actually both positive. But one, okay, so I was expecting one to be negative, but both positive, but probably one is beyond our domain. It's too much of a cut. So sometimes you get surprised. So now we just need to use our tools, second calc. Let's find the zeros. What's the left bound? There we go. That's a good left bound. And then I go to the other side. There's a good right bound. I hit enter. So 1.31, it rounded to 2 decimal places. Again, whatever, how accurate can you cut? That's probably about it. And then, so let's remember that one. And then let's go find the other one. Second calc. Let's find the 0. And so 1.3, what did we say, 1.31? That's a good left bound. And then I'll go to the other side. There's a good right bound. And I hit enter. 5.36. This is the amount of the cut, right? 5.36. We're going to write these two down. So let's come back. Where is it? Here we are. So we kind of, let's not do that. Let's just solve that x is equal to, I think it was 1.31. And we also got x equals 5.36. So we might just jump in. It's okay, 2 answers, blah, blah, blah. Boom. Let's find the volume. That's it. But this is a place where now we want to look back to that domain question that they asked here. What is the domain of the function? So if I have a side that's 6, could I cut off 2 sides that are 5.36? No, I don't have enough room there. The maximum cut is 3. So x is something that has to be less than, actually, you could do less than or equal to 3, but I mean, if you make each of them 3, there's nothing left. You cut everything off. And it's got to be bigger than 0. So we talk about that. And that's what I thought we have to worry about. But no, this is the case. One cut's way too big. So we throw it out. And again, we do this a lot with logarithms and stuff. We get this extraneous solution that doesn't make sense in the real world. So always look that the solution's got to fit within the domain of what we're doing. So we've got this. And now let's see, what is our question? So we've kind of answered this question. That's the B question. And notice this is just how I think. This is how, actually, I took calculus twice as an undergrad because I got C's the first time and I was trying to be an engineer like you all. And to get into engineering school, you needed A's. So the second time I took it, I had a dyslexic professor who helped me, and I found out that's kind of how I think too. So he taught in this way, and again, what he taught more was not just the techniques of doing things, but the problem solving. So I am a little bit over the board and a little messy, but that's how problem solving, at least for me, it is. So I hope it's helpful for you, and that you feel able to just, we're just playing around. Now, if I had to write this up for a paper, yes, I'd come back and I'd make it all pretty and all that kind of stuff. But this is not a report. This is just us working through problems. So now I can come and I take this earlier information and I can calculate that the length is going to be 14 minus 2 times 1.31. The width is going to be 6 minus 2 times 1.31. And the height is going to be 1.31. And that's what they want, the dimensions of the box. So we carry this one out. 14 minus 2, 1.31. I got that that's going to be a length of the box is going to be 11.38. The box of the width of the box is going to be 6 minus 2 times 1.31. I come up with 3.38. And then this one's already done. So this is our answer to the C part. Okay. Good. So again, all of these, once we get it set up, which is sort of the harder part, take its derivative, which sometimes can be, and set it equal to 0. Sometimes that solution, we're going to go into the technology because, it's going to give us an exact value. Now, is this going to be a pretty box? This might not be what our customer wants. They want it to fit on the shelf. So this will give us our maximum volume, but it might not be the one we settle on. We might want to make it 11 inches by something, So that's a different story. That's design issues and stuff. But we've at least provided the information. This will maximize the volume inside the box. We doing good? How are we on time? Oh, geez, we're almost done. He said I didn't have to finish, so I think there's one more problem, but he says he'd pick up where I left off, and I thought I'd get them all done, but what I wanted to do is get you this process. The other ones are similar, and he'll finish up with the next ones after this, but thank you for your attention, and hope it was helpful. Thanks. Thank you.